Module 4, Section 9.2, Sum and Difference Identities. Before we begin, let's investigate the following. If we let angle A be 30 degrees and angle B be 15 degrees, we want to look at what happens if we do the cosine of A minus B. Is that going to be equal to the cosine of A minus the cosine of B? So we have the cosine of 30 degrees minus 15 degrees, which would be the cosine of 15 degrees. And we want to see, is that equal to the cosine of 30 degrees minus the cosine of 15 degrees? Cosine of 15 degrees, when you evaluate that on your calculator, will give you about 0.966. We want to see, is that equal to cosine of 30, which is about 0.866, minus 0.966. When we work this out, we'll get negative 0.1. So we see that this is not equal. Let's try the same thing with addition. We want to do the cosine of A plus B, and we want to see, is that going to be equal to the cosine of A plus the cosine of B. So now we have the cosine of 30 plus 15 degrees, which is the cosine of 45 degrees. And we want to see if that is equal to the cosine of 30 degrees plus the cosine of 15 degrees. Now when we evaluate the cosine of 45 degrees on our calculator, we'll get about 0.707. And we want to see, is that equal to 0.866 plus 0.966? Well, when we add up that side, we'll see that we get a value of about 1.832, and that is not equal. So since neither one of them are true, we need to find another way to do our sum and difference when we're dealing with trig functions. So we have sum and difference identities. First, let's look at cosine. We see that cosine of our difference, A minus B, is cosine of A, cosine of B, plus sine of A, sine of B. And you see that when we're adding first, then we have subtraction. So the sign changes. So a good rule of thumb, a way to remember these, is cosine of your first angle, cosine of your second angle, then sine, change, sine, sine. So kind of like a cheer. Cosine, cosine, sine, 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 when you're doing cosine, sum, and difference. So let's do an example. We want to find the exact value of the following. First, let's do the cosine of 15 degrees. We can rewrite 15 degrees as 45 degrees minus 30 degrees. I chose those two because those are two angles that we know using our right triangles. So we'll split it up, and we have cosine 45, cosine of 30. The sign changes to plus, and then we have the sine of 45 and the sine of 30. So let me do our right triangles here. When we're dealing with 45 degrees, remember that our right triangle gave us the values square root of 2 over 2, square root of 2 over 2, and 1 here. And then when we have 30 degrees, the side opposite 30 degrees was 1/2. The side opposite our 60 degrees was square root of 3 over 2, and then our hypotenuse was always 1. So the cosine of 45 degrees would be the adjacent over the hypotenuse, or just square root of 2 over 2, times the cosine of 30 degrees, which would be the square root of 3 over 2, plus the sine of 45 would be the opposite over hypotenuse, or square root of 2 over 2, times sine of 30, which would then be 1/2. So we end up with the square root of 6 over 4 plus the square root of 2 over 4. And since we have the same denominator, we can put our numerators together, and we have the square root of 6 plus the square root of 2 over 4. Now let's use pi. We want to switch to radians, so we want to find the cosine of 5 pi over 12. So we can write 5 pi over 12 as 3 pi over 12 plus 2 pi over 12. And those reduce down to pi over 4 plus pi over 6. So we now have the cosine of pi over 4 plus pi over 6. So that will be cosine of pi over 4, cosine of pi over 6, minus sine of pi over 4, sine of pi over 6. Remember, pi over 4 is simply 45 degrees, and pi over 6 is 30 degrees. So we can use the same two triangles and basically the same values that we've got from example A. So we have the square root of 2 over 2 times the square root of 3 over 2 minus the square root of 2 over 2 times 1/2. And so we'll get the square root of 6 over 4 again minus the square root of 2 over 4. And putting that together, we get the square root of 6 minus the square root of 2 over 4. Now let's look at sine. When we're dealing with sine, we see when we have the sine of a plus b, it's sine of a cosine of b plus cosine of a sine of b. So the sine stays the same as what it was. And when we're dealing with sine, then we have sine, cosine, cosine, sine. So that's one way to kind of remember it. And just remember that the sign stays the same. So let's look at an example. We want to find the exact value of the following. First, we want to do sine of 75 degrees. So we'll split that up as the sine of 45 degrees plus 30 degrees. And so that becomes sine of 45 degrees cosine of 30 degrees plus, sine stays the same, the cosine of 45 degrees, sine of 30 degrees. Now, using our triangles from before, I'll repeat them over here. We see that sine of 45 was square root of 2 over 2. Cosine of 30 is square root of 3 over 2. Plus cosine of 45, which is square root of 2 over 2. Times sine of 30, which is 1/2. So we have the square root of 6 over 4 plus the square root of 2 over 4. And so we get the square root of 6 plus the square root of 2 over 4. Now for this example, we're going backwards. Notice that it's already been expanded for us, and we want to go back to one function with our angles being added. So sine, cosine, cosine, sine, and we notice we have subtraction, so this will be the sine of our two angles being subtracted, so we have 40 degrees minus 160 degrees. That is equal to the sine of negative 120 degrees. Now there's a couple ways we can go at this point, so we'll split off. One way is using the negative identities. We know the sine of a negative angle is simply equal to negative sine of the positive of that. And sine of 120 degrees would be the square root of 3 over 2, square root of 3 over 2. And we'll simply make it negative. Now another way to go would be to use the coterminal angles and say that the sine of negative 120 is equal to the sine of negative 120 plus 360, which is equal to the sine of 240 degrees. And that is also negative square root of 3 over 2. So either way, you'll get the same answer. Now let's look at tangent with a sum and difference. Tangent of a plus b is the tangent of a plus tangent of b over 1 minus tangent of a tangent of b. And with subtraction, it's the same. The signs change in the numerator and the denominator from what they were previously. So let's do one example using tangent. We want to find the exact value of tangent of 7 pi over 12. Now 7 pi over 12, we can split that up as 4 pi over 12 plus 3 pi over 12. And so that is going to be equal to pi over 3 plus pi over 4. So we have the tangent of pi over 3 plus pi over 4, which is equal to tangent pi over 3 plus tangent pi over 4 over 1 minus tangent of pi over 3 tangent of pi over 4. So using our triangles, remember that pi over 4 was the same as 45 degrees. So we had square root of 2 over 2, square root of 2 over 2, and 1. And then now we'll switch to pi over 3, which was 60 degrees. So we have square root of 3 over 2 over here now, 1/2, and 1. And remember that tangent was the opposite over the adjacent. So, kind of off to the side here, if I want to find the tangent of pi over 3, I know that it is the square root of 3 over 2 divided by 1/2, or simply multiply by 2 over 1. So we get the square root of 3 over 1, or square root of 3. And if I want to do the tangent of pi over 4, I'll get the square root of 2 over 2 divided by the square root of 2 over 2, or simply multiplied by 2 over square root of 2. Now all of these will cancel each other out and give us 1. So when we're working this out, tangent of pi over 3 was square root of 3 plus 1 over 1 minus the square root of 3 times 1. So we end up with the square root of 3 plus 1 over 1 minus square root of 3. Now we want to rationalize this denominator, so we're going to multiply the top and the bottom by 1 minus the square root of 3. Excuse me, 1 plus the square root of 3. Now when we do this, in the numerator we'll get the square root of 3 plus 3 plus 1 plus square root of 3, and in the denominator we'll get 1 minus 3. So we have in the top 4 plus 2 square root of 3 over negative 2, and when we split these up over each of our denominators, we have 4 over negative 2 plus 2 square root of 3 over negative 2. So we end up with negative 2 minus the square root of 3 as our final answer. Now let's look at another way we can apply these. We want to write each function as an expression involving functions of theta alone. So first we have the cosine of 180 degrees minus theta. So we'll use our sum and difference. We have cosine 180, cosine of theta, plus, sign changes, the sine of 180, sine of theta. Now remember, cosine of 180, that's basically cosine of pi, so cosine of 180 is negative 1 times cosine of theta, plus sine of 180 is 0 times the sine of theta. So 0 times sine of theta goes away, and we end up with -1 cosine of theta, or negative cosine of theta. Now let's look at sine. We want to find the sine of 30 degrees plus theta in terms of theta alone, so we rewrite it as sine of 30 cosine of theta plus, since the sine stays the same, cosine of 30 sine of theta. Now remember from our previous examples that the sine of 30 degrees was 1/2 times cosine of theta plus, and the cosine of 30 degrees was the square root of 3 over 2 times the sine of theta. And since nothing disappears as it did in the previous example, that's our final answer. And lastly, let's look at tangent. We're subtracting here, so when we rewrite it, we'll have tangent 45 degrees minus tangent of theta over 1 plus tangent of 45 times the tangent of theta. Now remember from before that the tangent of 45 degrees was 1, so we have 1 minus tangent of theta over 1 plus 1 times tangent of theta. So that gives us 1 minus tangent of theta over 1 plus tangent of theta. Let's look at one last way that we can apply our sum of difference identities. We want to find function values and the quadrant of a plus b. Suppose that a and b are angles in standard position, with the sine of a equaling 4/5 and a being between pi over 2 and pi, so we know that a is in quadrant 2, and cosine of b is -5/13, where b is between pi and 3 pi over 2. So b is in quadrant 3. We'll want to find each of the following. First, we want to find the sine of a plus b. We know that that is equal to the sine of a cosine of b plus cosine of a sine of b. Now in this, we've already got the sine of a. We know that it's 4/5. And we've got the cosine of b. We know that it's -5/13. So we need to find the cosine of a and the sine of b. Now there's two ways we can do this. We can use our triangles or we can use our identities. So let me show you both. First, let's use the identities. So we know that the sine squared of b plus the cosine squared of b is equal to 1. And we know that cosine of b is -5/13, so we're trying to find the sine of b here. So we plug in -5/13, which we want to square. So we have sine squared of b plus 25 over 169 equals 1. So we'll subtract that from both sides, and we have that the sine squared of b equals 1 minus 25 over 169, which, when we do that subtraction, will be equal to 144 over 169. So now we're going to take the square root of both sides. So we have that the sine of b, and remember that b is in quadrant 3, sine of b will be equal to 12 over 13, but sine is negative in quadrant 3, so we know that it's negative. So we have -12 over 13. And now let me show you how we can find the cosine of a, but let me use our triangles. We know that angle A is in quadrant 2, so we draw our triangle, always using the x-axis with our reference angle here for quadrant for quadrant 2 for angle A. And we know that the sine, which is the opposite over the hypotenuse, was 4 over 5. And using the Pythagorean theorem, we would have a squared plus b squared equals c squared. And we want to solve to find b here. We'll end up with 3, or if you know your Pythagorean triples, this is a 3, 4, 5 right triangle. But because we're on the negative side for our x values, we know this has to be a negative 3. So when we want to find, remember this is a, we want to find the cosine of a. The cosine of a was the adjacent side over the hypotenuse. So we have negative 3 over 5. You could also do this using the Pythagorean theorem, the identities here, as we did with b. So we have negative 3/5 for cosine of a. Now when we work these out, we'll end up with negative 20 over 65 plus 36 over 65, and that will give us a value of 16 over 65 for the sine of a plus b, and it's positive. Now let's find the tangent of a plus b. So that'll be equal to the tangent of a plus the tangent of b over 1 minus tangent of a, tangent of b. So remember using our triangles from before with a, we had negative 3, 4, and 5. Now if we do the same with b, b was in quadrant 3, and we have cosine, which is negative 5 over 13, and we know with our Pythagorean triples, or we've found that the sine was negative 12 over 13, so we know that this value is negative 12. So let's find the tangent of a is going to be the opposite over the adjacent, so we'll get 4 over negative 3, or negative 4/3. And then we want to find the tangent of b, which would be the opposite over the adjacent. So we have negative 12 over negative 5, or 12/5. Over 1 minus negative 4/3 times 12/5. So when we work out the top, the common denominator is 15. So we get negative 20 over 15 plus 36 over 15 divided by 1 minus negative 48 over 15. So we see we get 16 over 15 divided by, when we work out the bottom, we'll get 63 over 15. So we'll now just multiply by 15 over 63. So we'll get a value of 63 of 16 over 63 when we have our tangent, and that's positive as well. The last part we want to do is find the quadrant of a plus b. Since both sine and tangent are positive, the only place that that's true, so I'll write that out, both sine of a plus b and tangent of a plus b are positive, that only happens in quadrant 1. So we know that quadrant 1 is where a plus b lies.